statistics. It is time for a little bit of discussion in section 7.2, estimating a population mean. I'm going to jump over to my other camera here in just a moment, and we'll get going. All right. Now, before I get going, I'll remind you that the process is we like to go ahead and read the text, view the PowerPoint presentation, take a look at any supporting material in the Canvas modules, and then take a look at the homework questions. This really requires a lot of just practice, so we know where all the stuff is on our calculator, etc. So please do take a look at those questions and email me or post a question or two on our discussion board. All right, so section 7.2. This is where we will estimate a population mean. We use X bar to estimate mu. X bar is our sample statistic. Mu is our population mean. That's a parameter. Sample statistics will estimate population parameters. The point estimate is X bar. That's what we use to start the process. It's our best guess and our only guess, really, as to what mu might possibly be. That point estimate always comes to us from a sample. If I have a point estimate, I have something from a sample. The basic tool we use is the central limit theorem. The central limit theorem gives us the justification for using a sample to estimate a population parameter. You can go ahead and review that at the end of chapter 6 when you have a chance. There are requirements for this process to have validity. The requirements are that we have a simple, random sample. That is the first requirement. The second requirement is that either one or both of the following requirements are fulfilled. Either n is greater than 30 or my population is approximately normal. If those two requirements are fulfilled, then we can use the central limit theorem to justify using X bar to estimate mu. The construction is similar to what we did in 7.1. We start with the point estimate, and then we generate the margin of error. The formula here is a little bit different than the formula we saw in 7.1. We use a different distribution here. I haven't talked about this one yet. I will now. My margin of error is equal to T of alpha over 2 times S over N. The T value here is the critical value from the T distribution. Now, this T distribution is new. We have not used this before, but it is very, very similar to the Z distribution. And if you read the 7.2 material, they'll go through the similarities and some of the differences. One of the biggest differences is the fact that this t distribution relies on what we call the degree of freedom. Now, this degree of freedom is a very important notion when it comes to describing the physical world. It has a lot of different contexts and a lot of different forms. For us, we use the degree of freedom, df, equals n minus 1. And that's what we use in this circumstance. In a couple of other circumstances, we might use something different later this semester. Now, my confidence interval that confidence interval is given to us by starting with the point estimate x bar and adding and subtracting a bit, that bit being the margin of error. In its formula form, it looks like x bar plus or minus t alpha over 2 times s over the square root of n. Now, most of the time, our calculator will be able to work with this directly. Sometimes I may wish to calculate the margin of error myself for whatever reason. We have something called the T inverse 83 program that does that. It's very similar to the inverse normal program. So if I do happen to need the T of alpha over 2, I can go ahead and get that. In general, though, I will usually use on the TI-84, I usually use the T interval tool. That T interval tool lives under the stats key on the far right under tests, somewhere down there in the nether regions. We'll take a look at an example right now. The first example is very, very basic, no fancy stories. I think we're going to be measuring miles per hour speed of cars or vehicles. In any case, we have a random sample. And that random sample looks like, well, let's see, n equals 39. X bar equals 61.2 miles per hour, and S equals 4.7 miles per hour. We are going to build in this particular example the 95% confidence interval. Now, before I go through the keystrokes and build that, we need to check the requirements. Do I have a simple random sample? Is that the case? Simple random sample? Yes, I do. Either or, n greater than 30 or a normally distributed population. In this case, my sample size is n equals 39, which tells me that I've met the requirements for the construction of a confidence interval. Now, my calculator comes over to play. I turn him on, and under stat, over under tests, I find T interval. I have statistics. In this particular case, the mean is 61.2 miles per hour. 4.7 miles per hour is my standard deviation. 39 is my sample size, and I'm building the 95% confidence interval. Mr. Calculator tells me that, well, I've got a 59.7 to 62.7 confidence interval. I'm going to take one decimal place. It's the same as I see here. I will also note that my summary data is refreshed here on the screen so I can check my work. So 59.7 miles per hour less than mu. less than 62.7 miles per hour. So there's my first example. My second example is a little bit different. My second example works with raw data. And again, I have a random sample. This time we have a newborn baby weight. And that weight will be in pounds. I'll note that baby weight follows a normal distribution. And I'm going to build, in this case, the 90% confidence interval. My data, first little baby, 5.6 pounds. Second little baby, 4.9 pounds. 9.2 pounds, oh, big baby. 7.6 pounds, oh, the cute one. 7.4 pounds and 7.3 pounds finishes up my sample. Now, again, I need to check. I'll note that I have a random sample. That certainly is well represented. I'll also note that my population is approximately normal. So even though I have a small sample, I'm going to go ahead and rely on the central limit theorem because baby weight is normally distributed. So I'll take my calculator. I'll need to input my data. Oh, look, there it is in list one. This time when I pick up the T interval test, I'll point it at raw data. My data lives in list one, so I'll point it there. And I'm constructing the 90% confidence interval, so 0.90 goes in. My calculator will tell me a couple of things. Let's see, I've got raw data, so I'm going to take one more decimal place. So I'm going to write this with 2 decimal places. We have 5.29 pounds less than mu less than 8.04 pounds. I'll also note the mean, 6.67 pounds, the standard deviation, 1.67 pounds, and my sample size. This may be important for future analysis. So now we work through a couple of examples. I have one last thing to convey, and this is somewhat subtle. We're going to talk now about the effects of a couple of different aspects of your confidence interval construction. There's really 2 things the researcher controls when he builds a confidence interval, just 2. So the first thing we will do, we will look at the effects of the level of confidence. Now, for this level of confidence example, I'm going to use the same sample a number of different times. We'll have an X bar of 100, S of 15, and I'll have a sample size of 40. Now, I'm going to build 3 distinctly different confidence intervals. I'm going to build a 90% confidence interval, a 95% confidence interval, and a 99% confidence interval. And then we're going to take a look at what happens. On my calculator, as I say, I want this to be example heavy, so this time I've got summary statistics. My mean is 100, my standard deviation is 15, sample size is 40. We're constructing the 90% confidence interval. So rounding to the nearest whole number, 96 to 104. Now, I'll run that analysis again, changing only the level of confidence. And when I run it the second time, that confidence interval grows to 95 to 105. When I run it a third time, it grows a final time from 94 to 106. So at the end of the day, I can take a look at this, and it's fairly clear that a higher level of confidence will lead to a wider interval. The way I like to look at it, so I've got to use a bigger net to increase the chance of catching a fish. Now, the other effect that we have sample size. I can decide how large my sample should be. That was one of the reasons for the sample size determination, by the way, in section 7.1. So for this particular example, again, I'm going to use a sample with a mean of 100 and a standard deviation of 15. This time I'm going to keep the confidence level equal for all my examples at 95%. And what I'm going to do is I'm going to take a look again at a couple of different examples. N equals 40, N equals 100, and N equals 1,000. I'll run through the same set of keystrokes as I've done before. You've seen a number of them now. I keep the confidence level at 95, but I change my sample. So one last little example here. The mean is 100, standard deviation is 15. I'll start with a sample size of 40 and confidence level of 95%. So when I run through this a number of times, the only thing that's going to change is the sample size N. We've already done this. That's right over here. So 95 to 105. If I redo this with a sample of size of 100, that confidence interval tightens to 97 to 103. And if we jump all the way up to a sample size of 1,000, 99 to 101. I think it's fairly clear here that the larger sample leads to a tighter interval. The way I look at it in this case is the more times you go fishing, that's right here, the better the chance is you're going to catch the fish you really want. So, at the end of the day, you have a number of different examples there, and I will ask that you provide feedback and ask questions. Thank you, and goodbye for now.